Hello everyone, today we will be learning about the strength and concentration of acids. So in this section we will be comparing the strength and the concentration, also learning about factors that affect both the strength and the concentration of the acid. So we'll first look at the strength of the acid. Strong acids fully ionize in water, meaning that they will produce more charged particles. Now we did learn about this before in the previous lesson, but we're introducing charged particles here because if, for example, we have HCl ionizing, it forms H plus ions and Cl minus ions, which means that H plus ions are charged and HCl minus particles are also charged. But if you look at weak acids, only partial ionization occur, producing fewer charged particles. So for example, we have acetic acid here, produces a hydrogen ion and an acetate anion. So as you can remember from last lesson, we did both of these, but now we're talking mainly about charged particles because we did realize that the H ion is a charged particle. Now let's look at these two diagrams and try to work out which one is a strong and which one is a weak acid. So let's look at this one, for example. You can see that the charged particles or the particles are all separate. Very few, almost all are ionizing, which means that this is a strong acid. Now while here we don't have all the acids or the particles separated, here we have still a combined particle. And we have a lot of those, meaning that complete dissociation or complete ionization is not occurring here. So this is a weak acid. So you can see the strong and the weak acid and you're able to compare them. Now let's move on to charged particles. Now charged particles, as I stressed earlier on, they're charge carriers. In other words, a charged particle is able to carry a charge, and for this reason they're used as electrolyte. More charged particles means a better electrolyte. So for example, here we have more charged particles. We have more particles that are all released. Now note that these are acid particles, and when they're released they produce a charged particle. So for example, they produce a cation as well as an anion. And in here we have a lot of those. But this is compared against this, which has fewer charged particles, meaning a poor electrolyte. So for example, here we have more of these acid molecules and less of the charged particles, meaning that this is not able to carry much charge because the charged particle concentration in this for example is more and this is less, making this a better electrolyte and making this a poor electrolyte. Now it's testing for electrolytes. Now in school or even as a demonstration, you might test for electrolytes or test two electrolytes against one another. And here we have a setup, and this is a very good setup and may be used in school as well. So here we have the two setups where we have an AC or a DC battery, two globes, or we can use the same globe, it doesn't matter, but to compare it easily and against one another we would use two setups like this against one another. So here we have the two globes and we have two beakers, each containing two different electrodes or two electrodes, the metal, and wires connecting them all. So note that the electrodes are inert because we do not want them to react with the electrolyte. So the inert electrodes, maybe platinum electrodes, are used. So here we have the non-electrolyte solution, which is a blue, and also the electrolyte solution. So we're comparing the two. So our independent variable would be the non-electrolyte and the electrolyte. So what would be our variable? Our dependent variable here would be the glowing or the brightness of the globe. Now let's see what a non-electrolyte would be. just learning, just getting from the stuff we learned just then, we know that non-electrolytes are going to be weak acids. In other words, they do not completely dissociate. Therefore, there's going to be less charged particles. So for a non-electrolyte, you are going to be using a weak acid. Well, for an electrolyte, you're most probably going to be using a strong acid, such as hydrochloric acid. So clearly, these two are what we'll be using. Now, we would connect one of the electrodes to the lamp and connect the other side of the lamp to our battery, and this is to the negative terminal. And we'll connect one other electrode directly to the battery, so it's all a complete circuit. Now the circuit here, so there are going to be charged particles here that are going to carry the charges from this electrode to the other electrode. So that's how the electricity is going to flow across. Now this has the same setup. So we would have one electrode connecting it to the lamp. The lamp from the other side is connected to the battery, and the circuit is completed when another electrode is connected to the battery. And again, if you have charged particles here, they would conduct electricity. The globe glows brightly when good electrolytes are tested. Now this is an electrolyte, while this is a non-electrolyte. So assuming that this has more charged particles, as it does because it's an electrolyte, the globe is going to be brighter here than this. And you can see that gold rim to show the brightness. So here's the difference. Now, so we can see that the charged particles here are going to be the charge carriers. Remember I told you that electrons are charge carrier, are the electricity, so the flow of electrons. Electrons are charges. So they are going to be flowing from here. The charge is going to flow from here to here. And the positive charge is going to flow through the charged particles we have here. And in an electrolyte solution, there are more charged particles. Now let's look at bases now. Bases have a very similar approach because we're looking at the dissociation of it. So strong bases dissociate more readily. So therefore, acting as better electrolytes, example, sodium hydroxide. The sodium hydroxide is a strong base, meaning that it fully dissociates. In other words, all of the base molecule is going to disappear or dissociate into its cation and its anion. Now weak bases only partially dissociates. So clearly, partially dissociating, therefore acting as poor electrolytes because there's not going to be enough charged particles. So for example, we take ammonia as a weak base. Now factors affecting the number of ions in solution: the strength of the acid and the concentration of the acid. And this is what we'll be mainly focusing on our lesson. The strength is how well it ionizes. As you can see here, this part is not ionizing very well. However, this part has all ionized because they're all separate. See, from this lattice, it has all separated, meaning that this is not a very strong acid, while this part shows a stronger acid. The concentration of the acid. Now the concentration is how many molecules of the acid is present. So clearly you can see that this is a concentrated solution, but again, concentration is a comparison to something, so you would have to compare this against something else to see whether it's more concentrated or less concentrated. The strength of the acid. The strength of the acid is the tendency of the acid to donate protons. Now we looked at this in our last lesson, but again, protons are H plus ions, which is hydrogen ions. Therefore, in a strong acid, more protons are donated, meaning that more ions are present. So for example, HCl, more protons are donated because all the HCl particles or molecules are able to donate their proton. So there's obviously going to be more ions, better electrolyte. However, in a weak acid, less protons are donated, meaning that there's going to be less ions present. Ions meaning charged particles. so it's not a good electrolyte. The concentration of the acid. The concentration of the acid is the number of ions per unit volume. Now this is looking at the concentration, so it is the number of ions in a unit volume. So for example, let's say we have a square like this, and how many particles are in it, and that's what the concentration is. In a concentrated solution, the number of ions per unit volume is high. So if something is concentrated, which meaning it's going to have a higher unit volume. So for example, we have glacial acid, which has concentrated ethanoic acid. And we know it's concentrated ethanoic acid because this substance is corrosive, while ethanoic acid is a weak acid. So if it's corrosive in a weak acid, there's going to be a lot of such particles, meaning that glacial acetic acid is going to be a concentrated acid. While in a dilute solution, the number of ions per unit volume is low. So let's take that square again. We have a square like this, and we're going to only have few particles. Therefore, this has less units per unit volume, meaning it's a dilute solution. So for example, vinegar, it has only 4% ethanoic acid. That means only 4 molecules from 100 molecules are acetic acid molecules. So it's not corrosive and it's used for food. So clearly you can see the difference. One is corrosive because it's concentrated, while the other is not corrosive because it's dilute. Ionization in a strong acid. Now we'll be focusing on strong acids at this point. In a strong acid, monoprotic, which is a monoprotic acid. Now we'll come across this later in this lesson, but we'll move on for now. And the concentration of the acid equals the concentration of the hydronium ions. Now in other words, let's take this for example. We have HCl. The concentration of the hydrochloric molecules are going to equal the concentration of the hydronium molecules. So initially this beaker would have contained three hydrochloric molecules, because all of that 3 hydrochloric molecules have dissociated to form 3 hydronium atoms, hydronium ions, and 3 chloride ions, as you can see. Now let's look at the ionization of a weak acid. In a weak acid, the concentration of the hydronium ions produced is going to be less than the initial concentration of the acid. So for example, here we can see that there were 3 HF molecules. So for example, we only have 3 HF molecules, and then we only have 1 H3O plus and 1 F minus, meaning that out of the 3, only 1 of them dissociated. So clearly our concentration of the HF or the acid molecule is going to be less than the concentration of the hydronium molecule. So the initial concentration of the acetic acid molecule is going to be greater than the final concentration of the hydronium ions. Concentrated solutions of acid. So let's compare 2 different acids. We have HCl and HF. So hydrochloric acid is a strong acid, while HF, which is hydrofluoric acid, is a weak acid. So as a strong acid, this would fully dissociate or ionize in water. So all of the acid particles have ionized, forming 1, 2, 3, 4, 5 hydronium ions and 5 chloride ions. In this case, we have the same number of molecules. In other words, we have 1, 2, 3, 4, 5 acid molecules. Out of the 5 acid molecules, 2 of them have dissociated, while 3 remains still as acid molecules. Meaning that these 2 here are both concentrated because there are 5 of them. However, one is a strong acid, meaning all of the acid molecules have dissociated, while one is a weak acid, meaning only half or even less than half has dissociated. Now let's look at a dilute solution. We're taking the same solutions. One is hydrochloric acid, the other is hydrofluoric acid. In hydrochloric acid, we have H3O plus and only 3 molecules of them. So initially there were only 3 molecules of the hydrochloric acid molecule. So all 3 of them have dissociated to form 3 hydronium ions and 3 chloride ions, while in this case here we have 3 HF molecules. 1 of them have dissociated to form a hydronium ion and a fluoride anion, while 2 of them still remains as acid molecules. So this is a weak acid, only partial ionization has occurred. But again, comparing it to the dilute word, it has 3 molecules. It started off with 3 molecules. While the other one, the previous slide, we looked at 5 molecules. So clearly there are more molecules in a concentrated solution than in a dilute solution. Now let's calculate the extent of ionization. And the extent of ionization is also known as the degree of ionization. So the extent of ionization is given by a percentage. So the percentage of ionization would equal the hydronium ions at equilibrium, so the concentration of that, over the initial concentration of the acid. And we times the whole thing, the whole fraction, by 100 to get the percentage. So let's look at hydrochloric acid, for example. We know that hydrochloric acid has a 100% ionization rate because the hydronium ions equal the concentration of the acid. We'll work it out. We know that the degree of ionization is going to be equal to the hydronium ions at equilibrium. Now we know the hydronium, let's say for this one, 0.1 moles of HCl. So we know the initial concentration of the acid, it's 0.1. Now the hydronium ions at equilibrium, because this is a monoprotic strong acid, it's going to be 0.1 as well. Now this is going to be times by 100 to get the percentage. Now this and this would give us 1. So 1 times 100 gives us 100. And that's why the degree of ionization of hydrochloric acid is 100. Now we will look at a weak acid, because in a weak acid it's not going to be 100, it's going to be less than 100. And we're going to consider acetic acid for the time being. So we have 0.1 moles of acetic acid. And from that 0.1 moles, only 1.3 times 10 to the power of minus 3 moles per liter are going to be hydronium ions. So to work out the degree of ionization, we would first write the concentration of the hydronium ions. In this case, 1.3 times 10 to the power of minus 3 all over 0.1. 0.1 is the concentration of the acid. So we have 0.1 moles of acetic acid. That we're going to times by 100 to get 1.3%. So this is the degree of ionization of acetic acid, and this concentration of acetic acid. Now note that if the concentration of the acetic acid decreases or increases, then our value here is going to decrease or increase. Now this is a very important point later in the dot point. Now let's look at weak acids. We have, before ionization, we have the acid HX. HX, after ionization, there's going to still be quite a lot of HX left, but obviously going to be below 100. And we're going to have HX ions, just X ions, and hydronium ions left. So clearly there's going to be 3 products at the end, and this is in a weak acid. So in a weak acid, not all of the HX ions dissociate, but some of them do to produce hydronium ions and X ions. In a strong acid, this is different. So in a strong acid, we're taking the monoprotic HX ion acid here. in the monoprotic HX acid, we have all of the HX ions being dissociated. So that means we're going to have H3O plus. That means there's going to be completely all of the H3O plus, and we're going to also have X ions. So we're going to have X minus, and there's going to be 100% of X minus ions. So you can see that it has completely dissociated to form the same concentration of X minus ions and the same concentration of H3O plus ions, as you can see. Degree of ionization. In a strong acid, the percent ionization of the acid is 100%, which means percent, that means per 100. So, however, in a weak acid, the ionization is going to be less than 100%. We just looked at it just then. Now let's look at the degree of ionization. The more dilute the acid, the lower the number of ions and acid molecules per unit volume decreases. Now look at this, the strong acid and the weak acid have two different graphs. The concentration of the acid. As the concentration of the acid increases, we have the ionization rate being the same. It's going to maintain at 100% ionization for a strong acid. However, if the concentration of the acid increases for a weak acid, the ionization percentage is going to drop. And this is going to be in a hyperbolic curve like this. Because it's a fractional value, it's going to drop like that way. Now let's look at polyprotic. Now what does protic mean? An acid is classified using the number of hydrogens or protons it is able to donate. So for example, we have different acids that are able to donate different different number of hydrogens. So for example, we have hydrochloric acid, which is HCl. It has one hydrogen, as you can see. So it has to be a monoprotic acid, meaning only one of its hydrogens are able to be donated because it only has one of them. Let's take another example. We have sulfuric acid. Now sulfuric acid, the formula is H2SO4. So it's called a diprotic acid because both of these hydrogens here are able to be donated. So it's 2. Now mono stands for 1 and di stands for 2. We also have the third group, which is called triprotic. Now triprotic acids, 3 of the hydrogens are going to be donated. Now in this case, citric acid, there's C6H8O7. Now we have 8 hydrogens, but from that 8 hydrogens, only 3 are able to be donated. In other words, the other 5 cannot be donated in ionization. So in that case, it has 3 hydrogens that it can donate, making it a triprotic acid. Now we'll compare the monoprotic, the diprotic and the triprotic acid and how they ionize in water. Let's look at the monoprotic one first. It releases 1 hydrogen ion. So one of the hydrogen ions are released. When reacting with a base, they donate 1 proton. So if we look at this equation here, we have hydrofluoric acid. It's going to react with our base here, which is sodium hydroxide. Sodium hydroxide and hydrofluoric acid are in a neutralization reaction. In this neutralization reaction, they would form sodium fluoride and water. You can see that the hydrogen from here is donated to the sodium hydroxide, and the sodium hydroxide is displaced to give us sodium, fluoride and water. So it gives away its 1 hydrogen. So examples of monoprotic acids would be HCl, which is hydrochloric acid, nitric acid and hydrofluoric acid. Also comes CH3OCOOH. Now this is acetic acid and it is a weak acid. Note that it has 4 hydrogens, but only this hydrogen here is able to be donated, while these three remain and cannot be donated. Therefore, for that reason, it's called a monoprotic acid. Moving on to diprotic now. When reacting with a base, they donate two of the protons. So for example, here we have sulfuric acid, which is a diprotic acid. It reacts with sodium hydroxide. Now sodium hydroxide is a base, so they undergo a neutralization reaction to form sodium sulfate and water. So as you can see, when you're writing your equation, always write the states down and balance it. Now the ionization, however, happens in two steps, because realize that there are two hydrogens, meaning that each hydrogen is only one hydrogen is lost in ionization. So two of these ionizations have to occur to lose both of the hydrogens. So the first step, during the first ionization, they release their first hydrogen ion. So the first step is when hydrogen reacts with the water to form hydrogen sulfate ion along with a hydronium ion. Realize that this goes to completion because hydrogen sulfate is a strong acid. Then comes a second step where the second hydrogen is released. Now here's what we have as a product. Now this product, which is HSO4 minus, reacts with water. To produce our sulfate ion and a hydronium ion. Now again, always write your states, which is this is going to be aqueous, this is going to be liquid, this is again going to be aqueous, and aqueous here as well. Now let's look at this. We have hydrogen sulfate ion reacting with water. This is an ionization reaction. Note that it's going to be in equilibrium. It's going to be in equilibrium because this is a weak acid. So when it's in equilibrium, it would react to form hydronium ion and a sulfate anion. Always make sure your charges are correct. We have a charge of -1 on this side and a charge of -1 here because of the -2, adding another 1, giving us -1. So as you can see, this happens in two steps. The first goes to completion while the second one doesn't. So it's in equilibrium. Now let's look at triprotic acids now. Triprotic acids, when reacting with a base, they donate all 3 protons. So because they have 3 protons they can donate, they will donate all 3. So here we have citric acid will react with sodium hydroxide in a neutralization reaction, and it would produce this. So 3 of its hydrogens are being lost. So we have H5, and these 3 hydrogens would be gained by the sodium hydroxide here and produce water. Now the ionization, however, happens in 3 steps again. During the first ionization, they release the first hydrogen ion, then releases the second hydrogen ion, and lastly the third hydrogen ion. We'll look at this in step 4. Here we have citric acid reacting with water. It's in equilibrium because it's a weak acid to form C6H7O7 along with a hydronium ion. Now this product is reacting again with water, and it loses another hydrogen ion. This time it's going to gain another minus because it's losing a plus sign, so it's gaining a minus to form hydronium ion again. Now this product here again reacts with water. It reacts with water to form C6H5O7 with a 3 minus. Again, realize as you react with water, you're losing a hydrogen, and as a result you're going to lose a positive sign, meaning you're going to gain a negative sign. So you're left with hydronium ion, as you can see here. So this example is citric acid, and also citric acid is an example of a triprotic acid. Now let's look at monoprotic versus triprotic. Regardless of strong or weak acid, a polyprotic, that means a diprotic or a triprotic acid, solution will contain more protons than a monoprotic acid solution, even if the original concentrations of both solutions were the same. Now what this means is, for example, let's consider HCl. HCl has one proton that it can donate. In other words, if a beaker was to contain, let's say, one HCl molecule, and this goes into aqueous form, so it'll dissociate and it'll form one H plus and one Cl. But if we take H2SO4, now H2SO4 we know is a diprotic acid, and again this diprotic acid has two protons it can donate. Meaning, if you have a beaker with one molecule of acid, H2SO4, in aqueous solution, it will dissociate in 2 steps. Remember, ionization occurs in 2 steps for a diprotic acid, and it will have 2 hydrogen ions lurking along with 1 sulfate ion like this. So the concentration of the hydrogen ion here is going to be 1, while in here it's going to be 2, double. Meaning that the concentration of, even though the concentration of both of the solutions are the same, the acid molecules, for the acid molecules, this is going to be a stronger acid than this, because there's going to be a greater concentration of hydrogen ions than in this one. So as you can see, diprotic and triprotic, or the amount or the number of protons one acid can donate, also affects its strength. Now let's review back to what we just learned. We learned about the concentration and the strength of acids as well as bases. So with the strength and the concentration, we kind of compared the two. In other words, we compared how strength and concentration are interlinked, as well as how they're differed. Now let's look at some questions. We have question 6. It's a multiple choice question. We have 4 options here. Which of the following is incorrect? Note that incorrect is in bold. I did that, however, it might not come in your exam paper. So if you find it easier, always underline or bold it or highlight incorrect, just to make sure that you are answering it correctly. So we have 4 options here. We'll consider each option one by one. Option A. A solution of weak acid will contain more pronated acid molecules. Now a weak acid will contain pronated molecules because it only partially ionizes. In other words, this statement is correct because most of the molecules are going to have protons intact. In other words, it's not going to be ionized. So option A is correct, which means it's incorrect for our question here because it's asking for the incorrect statement, not the correct statement. Now let's consider option B. Option B says a solution of weak acid will contain a small number of hydronium ions. Now this is correct because a weak acid partially ionizes, which means it's only partially going to produce the hydronium ions it can. In other words, let's say it has a 25% ionization rate. So out of 4 molecules, only one of them would be a hydronium ion. Or out of 4 molecules of acid molecules, only one is going to be ionized to form a hydronium ion. So clearly that is a correct statement. In other words, it's not correct for our question here. Now considering option D, a solution of strong acid will contain nearly the same concentration of hydronium ions as its original concentration. Now this is a strong acid, in other words, complete dissociation. So it would contain the same amount of hydronium ions. So this statement is correct, making this incorrect for our question here. Now let's consider option C. A solution of strong acid will contain less number of hydronium ions than pronated acid molecules. Now this is an incorrect statement, because we have strong acid and it would contain more hydronium ions and less pronated acid molecules, and this is incorrect. Therefore, option C is our answer. Now let's move on to question 7. Question 7 is also a multiple choice question. Here we're given a diagram. Which diagram best represents the magnified view of a concentrated strong acid? Now here, concentrated and strong are our two important words. Concentrated means the amount of molecules per unit volume. So which of these four are concentrated? We'll consider each option one by one. Is it option A? Option A is not concentrated, it is dilute. But is it a strong or a weak acid? It's a strong acid, therefore option A is not the correct answer. Now moving on to option C. Option C, here we have, it's not strong. It's not strong because still we have ions or acid molecules intact, meaning not complete ionization has occurred. So is it a concentrated or a dilute solution? It's a dilute solution, comparing it to the others. So it's a dilute weak acid, which means it's not a concentrated strong acid, making option C incorrect. Now moving on to option D now. Option D says, this is our option D. Now option D is a concentrated acid, however is it a strong acid? To find that out, we look at the molecules. We still have these molecules that are intact. So we still have acid molecules that are intact, meaning not complete ionization has occurred, therefore it's a weak acid. That makes option D incorrect. Now let's consider option B. Option B here we have is concentrated, as you can see, and all of the molecules are not intact. In other words, they're all dissociated, making it a strong acid, complete ionization. Therefore, a concentrated acid contains a large amount of solute. A strong acid is fully dissociated into ions and no molecules remaining, making option B the correct answer. Now moving on to question 8 now. Again, question 8 is a multiple choice question. Which of the following equations is incorrectly expressed? Highlight incorrectly, because from here, 3 of them are going to be correct and 1 is going to be incorrect. Now we have to pick which one it is. Is it option A, option B, option C, or option D? We'll consider each option one by one. We have option A. We have H2CO3 plus water reacting to form the carbonates ion, and also a hydronium ion. So here we have a equilibrium reaction. Is it correct? Yes, it is. Because carbonic acid is a weak acid, this is correct. And this is a first ionization reaction. As you can see, it's only losing one of the hydrogens because it's a diprotic acid. So this equation here is completely correct, making this incorrect for the answer. Now option B has nitric acid reacting with water to form nitrate ion and also the hydronium ion. Now this is a complete reaction. In other words, it goes to completion. That's correct because it's a strong acid. Nitric acid is a strong acid. So option B is correct. And we can see that it only has one proton. So all of its protons are donated in the first reaction. Now option C has nitrous acid reacting with water. Now nitrous acid is a weak acid, so the equilibrium reaction here is correct. And this is the first ionization because, it's the only ionization because it's a monoprotic acid. So we have NO2 minus, which is the nitrite anion, and also a hydronium ion produced. So clearly option C is very correct, making it incorrect for the question. Now let's consider option D. Option D has sulfuric acid. Now the sulfuric acid is reacting with water to form a sulfate anion and a hydronium ion. Now note that sulfuric acid is a diprotic acid, making it, so it has to happen in 2 steps. Now as the first step, this is incorrect. One reason is that it's not going to completion. In the first ionization of sulfuric acid, it goes to completion because it's a strong acid. And it should have a hydrogen still intact because it's losing 1 hydrogen at a time. Therefore, D is incorrect because the diprotic sulfuric acid will undergo ionization in 2 stages. And this is an incorrect stage they have represented here. Therefore, option D is the answer. Now let's move on to question 9. Question 9 has 2 parts. First part, name a weak acid. Now this is pretty simple. It says name, so name is just to identify it with 1 word. So the example we have here is ethanoic acid or acetic acid, or you could have citric acid or lactic acid. So any of these is fine. But make sure when you're naming it, it's also important to know that you write the name instead of the chemical formula, because it says to name, you have to write its whole name instead of the chemical formula. And question B, it says to define the term weak in relation to acids. Now this is something we've been doing. Weak is a strength. So what is the strength? The strength of an acid is its ability to be ionized. A weak acid has a lower tendency to be ionized. So as a definition, you would have to provide a very simple, concise, yet very informative answer. So your answer should be concise but informative. So here it says a weak acid is not fully ionized in water. So you're gonna define the strength as well as how weak acids are defined. So that's how you would approach this question, which is in 2 parts. Now moving on to question 10. Using hydrochloric acid and citric acid as examples, describe the difference between a strong and a weak acid in terms of equilibrium between the molecule and its ion. So clearly we have to do some specific things in this question. One is to consider these 2 acids. One is hydrochloric acid and one is citric acid. So you should be familiar with these 2 acids and be able to identify which one is a strong and which one is a weak. So we know that the hydrochloric acid is a strong acid here, and also that citric acid is a weak acid. Now if you're considering about the equilibrium between the 2 and its ions, we know that a strong acid such as hydrochloric acid dissociates fully into its ions in aqueous solution. So here we have hydrochloric acid reacting with water to fully dissociate into the hydronium ion and the chlorine anion. So it goes to completion. That's why it's denoted by this arrow here. But in a weak acid, the citric acid, it only partially ionizes. In other words, it does not fully dissociate. There is an equilibrium established between the ionized and the molecular forms of the acid. As you can see from the equation, it's always good to include equations so your description is much more clearer. So we have the acid, which is Ha, reacting with water. Now it's in equilibrium because it's a weak acid, forming A- anions and the hydronium ion. So you can see it's in equilibrium because it's not a strong acid. In other words, not all of the acid particles are being ionized. So this brings us to the end of the lesson. That means that we just covered strength and concentration of acids, where we were able to define the strength and the concentration. We compared the 2, in other words, we looked at why strength of the acid differs from the concentration of the acid. We also learned how to calculate the degree of ionization.